All right, today we're peeling back the skin of an airplane to look at something you can't see but can't fly without. Its electrical system. It's basically a flying power grid. So let's get into it.
You really have to think about it. A modern plane isn't just a vehicle, it's like a small city flying miles above the Earth. It needs power for everything: the flight controls, the navigation, the cabin lights, even the little screen you're watching your movie on. So, where does all that juice come from?
Well, the whole system is an absolute masterpiece of engineering. See, unlike the power grid in your city, this one can't afford to go down, not even for a second. It's all about layers upon layers of backups and fail-safes, with safety as the #1 non-negotiable goal. To really get how it all works, we have to start where the plane starts, right there on the ground at the gate. Powering up the aircraft is this really careful step-by-step sequence.
So first, a big cable gets plugged into the plane from a ground power unit, or GPU. That's what runs the lights and AC while everyone is boarding, and it saves a ton of jet fuel. Then, right before pushback, you might hear this kind of high-pitched whine from the tail. That's the APU, the auxiliary power unit. It's a small jet engine that lets the plane generate its own power. And finally, when those huge main engines roar to life, their powerful generators kick in and take over the whole show for the rest of the flight. And at that moment, the plane is totally on its own. It's a self-sustaining power station, creating all the electricity it needs. But, making the power is really only half the battle.
Okay, so you've got all this power coming from the engines, now what? How do you get it to the hundreds of different systems all over the plane, from the cockpit to the coffee maker, and do it all safely?
The secret sauce here is something called a bus bar. The best way to think of it is like the main artery in the body, or maybe the main junction box in your house. All the power from the generators flows to these bus bars, and from there it gets sent out to all the different circuits that need it. But with that much electricity flowing around, things can go wrong. You've got shorts, overloads, all sorts of potential failures. Protecting the plane's wiring and all its equipment is just absolutely critical. Just like in your home, the plane has layers of protection. You've got simple, one-and-done fuses. You've got relays, which let a tiny switch in the cockpit control a huge amount of power somewhere else. But the real MVPs are the circuit breakers. If you've ever seen a picture of a cockpit, you've seen that huge wall of them. Each one is a little reusable switch that automatically trips and cuts the power if something goes wrong, preventing damage or even a fire. Now, for the really critical stuff, the plane's brain, basically, the protection has to go to another level. We're talking about the avionics, the flight controls. They're way too sensitive to handle the raw power surges that can happen on the main grid. So, what the engineers came up with is brilliant: a split bus bar system. It basically creates a separate, isolated, super clean power grid just for those sensitive electronics. This means a huge voltage spike from, say, starting an engine has no way of reaching and frying the critical flight computers. It's just genius design. And all of this really brings us to the absolute core philosophy of aircraft electrical design, and that's redundancy. The entire system is built so that no single point of failure can ever cause a total disaster. It's the whole name of the game. And a really easy way to see this is to just compare different planes. A small, single-engine aircraft, it has one generator and a battery for backup. Pretty simple. But a big, twin-engine airliner has at least two main generators. They share the workload, but here's the key. If one of them fails, the other one is more than powerful enough to take over and run everything essential without missing a beat. Okay, but what about the worst-case scenario? I mean, the one that keeps engineers up at night. What happens if you lose all the main generators? Is the plane just a glider at that point?
Nope, not even close.
This is where the layers of backup really shine. Instantly, onboard batteries kick in to power the most critical flight displays. Then, the APU, that little engine in the tail, can be fired up mid-flight to act as a backup generator. And if even that's not an option, there's one last incredible line of defense: the ram air turbine, or the RAT. It's a small propeller that drops down from the plane, and the wind just spins it like a pinwheel, generating enough emergency power to fly the plane and land it safely. So, the system is protected from physical failures, sure, but modern aircraft also have to be shielded from a whole world of invisible threats, electromagnetic hazards that could wreak havoc on their systems. And there's this whole alphabet soup of dangers they have to account for. You've got EMI, which is interference from other electronics. Then there's stuff like HERO, making sure powerful radio waves don't accidentally set off military explosives.
HREF is about preventing strong EM fields from igniting fuel vapor, and HRIP is all about protecting the people on board from harmful radiation. It's a hidden battle of invisible forces.
So when you look at the whole picture, from that first plug-in at the gate to the multiple in-flight backups, it's just this masterpiece of layered design. It's all about generating power, distributing it safely, protecting every single wire, and having a backup for the backup, and then another backup for that.
So the next time you're flying and you hear that steady, quiet hum in the background, that's not just noise. It's the sound of an incredibly complex electrical symphony performing perfectly with a single purpose: to make sure the power and the plane never go down.